Nice. So thank you all for letting me speak to you about this today. I'm presenting a lot of work done with my co-champion, Francis McCabe, and also a whole bunch of other people, some in attendance, working on the tool chains and runtimes. So as an outline, I'm going to start with motivation and requirements, and then spend some time kind of talking through the design space we considered, and then move on to kind of walking through the current state of the proposal, and then end with some next steps. So for the motivation, this has been a long and winding road leading here. Sorry. And it started actually with the question of how can WASM call web APIs without JS glue code? Because in the MVP we started with ultra minimal things saying, well, you can always just call through JS. But that's not great for performance and other reasons. So we started with this host bindings proposal. And this is 2017, right after WASM was kind of MVP was released. And we start with this kind of classic OS C-list approach where we say, okay, well, WASM only has the I32s, but we have these tables that are kind of not really accessible to WASM, but they're at the boundaries, and then the indices or the I32s are indices in the table implicitly, kind of like an OS process does. But we ran into a bunch of challenges as we started to work through all these use cases, and instead we kind of realized we're WASM, we have this cool safety and software isolation. We can do actual first class capabilities in the form of initially this extern ref, which is some opaque reference. You don't know what it's to, but you can't forge it, you can't see the bits, and then a bunch of first class ops for being able to move these into and out of tables. And now the WASM code can do it itself instead of needing the separate host bindings proposal. And this is pretty general approach, allows a lot of different things. With type imports as an extension, you can actually statically talk about the different kinds of external references and just references in general. And then there's all these extensions to GC, which is a whole separate line of investigation. So we spent a lot of time on that, leaving host bindings aside, but then came back to the question of, well, how do we call these web APIs efficiently? Because yeah, we have this extern ref, it lets us hold any JS value. So technically we can kind of create any JS value, and in doing so, craft any call to web API. But now you're doing like multiple calls just to create all the values before you actually make the calls. So it's not especially efficient, maybe even slower than JS glue code in the first place. So then the proposal morphed into round two, WebIDL binding, saying, okay, we're trying to call WebIDL. Let's just specialize that case. That's all we're trying to do here. And that's what we did for a little while. But then this whole WebAssembly outside the browser thing kind of started to take off, which was, from day one, a goal of WebAssembly is to not be dependent on running the browser, not have a hard dependency on JS or web. But we weren't sure if it would actually happen until it started happening all over the place. And so once that started happening, you add this interesting constraint of you can't assume that the host has JS or web APIs. So that led to a lot of different things. Wazzy saying, okay, well, what do we, if we don't have web APIs, what do we have? Saying, well, we're not just embedding in JavaScript. Let's think about those other languages we're embedding in. And a pure WASM kind of module ecosystem when we don't have this all-powerful JS API to link our modules together. So based on all that, we kind of rescoped and kind of said, well, let's design something just kind of for all this new growing set of use cases, and that was interface types. We renamed the proposal and kind of changed its scope. At the same time, kind of in parallel in asking some of these other questions, we worked on the module linking proposal, which is saying, okay, well, if I want to have pure WASM modules linked together, and I don't have JavaScript, what can I do? So that was the module linking proposal. And the module linking proposal added a lot of concepts that ended up feeding back into interface types that let us simplify and rationalize the design a lot better. And that's what I'll be presenting here today, which is this in this PR, this linking rebase. But it's not done. There's still more to do, and I'll talk about next steps. So I just wanted to give just a little historical perspective here. This is right. So talking a little more about the motivations, we want to make efficient web API calls. Reference types, form of extern ref, are great for passing DOM nodes and API objects, but not so good for values like strings, sequences, dictionaries, records, all these other things that are value types in WebIDL. One reason, you get this copy or several copies, you start with it in linear memory and you copy into a JS value that immediately becomes garbage. And then usually the browser then makes another copy into its internal format, which is, altogether wasteful. And then also there's this loss of static types. The WASM ends up calling into semantically this WebIDL ECMAScript binding layer, because that's the only thing that exists. And that's a very generic kind of dynamically typed binding layer that does a lot of extra work to recover the types that the browser wants on the other side. So that's inefficiency. So what do we want? Zero copy, or if not, a GC-free single copy in these calls. Zero copy when WASM uses kind of a canonical representation in linear memory that's kind of compatible with the browser kind of statically would want, but otherwise a single copy into a browser internal format that at least doesn't require a garbage collector to free. It can be kind of owned or immediately taken care of by the browser. So that's one use case. Another one is, how do we define Wazzy signatures? As we started to kind of work on Wazzy, we found there's not really a great way to express these signatures of these APIs in core WASM. For example, if you want to talk about strings or say lists of pairs of file handles and flags, there's not a great canonical way to do that. We want something that's efficient, whether using linear memory or future GC memory or opaque host references. We want to allow Wazzy interfaces to be virtualized by unprivileged WASM. It's like kind of a core value of, goal of Wazzy, and that means, we can't rely on kind of host magic powers. And also, just because you want to use Wazzy, you shouldn't be forced to import or export your memory, which is to say to not be able to encapsulate your memory. So that's Wazzy as a use case. And then lastly, there's this use case of creating maximally reusable modules in this kind of emerging pure WASM ecosystem. So a question, what profile do I target if I want to create a maximally reusable module? Like what do I make if I want to I just want to make some WASM, I want everyone else to be able to reuse it. For example, if I'm making like a grep.wasm, it should have pretty minimal dependencies, so I should be able to pretty maximally reuse this thing. Okay, well, Wazzy, maybe let's talk about the host dependencies, but how do I define the public interface for any non-trivial values that just aren't I32s? And there's multiple categories of clients that we want to support here. There's other WASM modules, there's native language runtimes, there's network filters, edge compute. There's a growing list of all these different places you might want to reuse this module. So there's currently, pre-interface types, no great answers, sharing linear memory and having an ABI for that, sharing GC memory and having an ABI for that, using glue code wrappers and like the embedding language. All of these kind of have problems, if you try to follow them through. I don't have quite enough time to like exhaustively explore each one. What do we want? One thing is kind of a realization after like thinking through the design space and kind of looking at what's already kind of succeeded is I think we want a shared nothing architecture where fundamentally these separate modules encapsulate their memory. And this is kind of the only successful precedent we've seen for actually composing languages that are kind of unrelated. And you see it with like, in the Unix small process style, connecting things with pipes, or in, more recently, the microservices style and connecting things with, gRPC and whatnot. They've really got to be at arm's length, and then you can meaningfully talk about composing them. But if you try to do anything more magically where they're like intertwined, I think it's not as a risky proposition. Also, or even though even if we do this shared nothing architecture, we want really low communication overhead between these things, because doing so will allow us to have finer grained modules and to be able to compose them without having, often what prevents a shared nothing architecture is there's so much overhead that, forces things to be put into the same, monolith. So a thing we can take advantage of here is the type synchronous nature of cross instance calls in WASM. So if we lean into that, then we can actually have pretty efficient basis of communicating between these shared nothing modules. So those are some use cases. Additionally, things we want, it'd be great if there were no kind of implicit ON copies where, depending on what the compiler was able to figure out, you may have this very large, potentially quite significant copy going on. We want a predictable kind of explicit cost model. We want to be able to support what's called API evolution, which is, you could also think of as subtyping, where you don't want superfluous breaking, major semver changes just because you compatibly extended signature, like you added an optional field to a record, would be an example, or an optional parameter. And a lot of existing interprocess protocols do support this. So this would be kind of just achieving parity in that respect. We want to design for a robust interoperable ecosystem, which means trying to avoid issues that would only emerge not when I'm developing a module, but only when I combine certain modules and then certain bad things happen that cause the problem. Because now nobody's in a good position to solve this. It's the poor user who hits this, not the author of either module. We want to still allow in contrast to shared nothing, shared everything linking, which is kind of classic dynamic native style linking for the reuse of stateless code. Like in particular, it should be possible to factor out a libc. You're not going to be able to factor out a shared nothing libc. It's kind of inherently a shared everything thing, and we shouldn't prevent that. I think we want to use a layered approach here, kind of in the layered in the sense of like HTTP is layered on TCP, layered on IP, WASM being IP in this metaphor. And the goal being just to keep WebAssembly, core WebAssembly simple. Fundamentally, we're talking about how WebAssembly modules interact at the boundaries with the outside world. It shouldn't force us, if we don't want to complicate the core model of what it means to do computation in core WASM. If all we really want to do is talk about kind of how it interacts with the outside world. So there's a kind of lot of axes of design space here, but one I'll look at is maybe, for lack of a more official term, explicitly typedness, where you have on one end of the spectrum, like here's some JSON, go nuts. And then, in increasing explicit types, there's a style with Protobuf where there's schemas, but they're implicit. There's another style interesting to look at called Avro, or a protocol called Avro, where the schemas are explicit, and then all the way explicit is these typed values, which is ultimately what we're doing in the proposal. So I'm not going to look at here's some JSON that wasn't really a contender, but I'm going to look at these two just because they're useful to contrast before getting to type values, which is the approach we're using. So the Protobuf style, this is a reasonable place to start. Why not just do protobufs? That's well demonstrated. It has a simplicity to it. You just pass an array of bytes. But actually, you actually want to pass some references too. You can't just serialize a reference into an array of bytes. So also we'll pass just an array of references too. But the challenge is, how do you pass this array of bytes and references? Or this is one challenge. Are you forced to import or export your memory? Well, that would break encapsulations, a thing we said we don't want to do. Maybe we add something to core WASM, like some sort of first-class view or slice, which is a thing we've talked about for a long time. So it's not necessarily a bad idea. But as a thing to use at the boundary of shared nothing modules, it has some challenges. Like in particular, after I share a view on my memory, what happens after the call is over? If I don't do anything, I just leave you with this dangling view. You can look at this memory for all time in the future, which kind of can lead to a class of use after free bugs, which definitely people see and hit when they today use typed array views and JavaScript to view WASM linear memories. So there are answers I won't go into, but there's not a fantastic one here. So that's one challenge. Another challenge is performance. It's hard to avoid having several copies here. So if I have this instance A and it has its own private representation of some pair of strings, and I want to send it to an instance B, I'm going to have to serialize it first, because chances are this private representation of the pair of strings is not the same as what the protocol serialization format mandates. So I'm going to have to copy there. And then I'll copy an instance B so it can deserialize into its own distinct representation, probably distinct representation of pair of strings. Now, maybe if I'm using a view or one of these slice refs, one of these where I can pass a view into A's memory, I can avoid this copy, that third copy. But that's actually, it's a maybe, because it's actually kind of hard, because a view is kind of a foreign concept from either a C or an LVM perspective. At C and LVM assume there's one big linear address space. A view is not in that address space, so you can't just manipulate this view with normal C code. You have to like hand code the WASM, or somehow specially generate the WASM to access the slice. So it's actually kind of a pretty big tooling lift to be able to avoid that copy, and might not be working full general, especially if you're trying to like literally reuse protobufs. So that's also a challenge. Another challenge is the interface schema you're using. The types, effectively the producer and consumer use, are implicit. So the question is, well, how does API evolution work? Because this is a thing that's supported by protobufs, and it works because the producer inserts runtime metadata into the byte stream that says, here's what I serialized. And the consumer looks at this metadata as they're deserializing it to say, okay, well, if you left out a field I expected, or you did something different, I can fix it up. And there's problems with this, I think. For one side, there's a code size cost. You have to have deserialization code in each module. There's a runtime cost because you're encoding this and decoding this metadata. There's a tension that you see because this protobuf isn't the only protocol. There's probably 5 options in this space, and so there's a tension between the flexibility of how much flexibility do you allow in the evolution versus the actual bloat and overhead required to deal with this on the decoding side. And there's a certain inflexibility, which is like once you stamp this binary format out, you kind of really have to stick to it over time, or it's a big change to like change the version of the binary format in a breaking way. And I think there's a fragility inherent to the ecosystem in that when you're debugging or creating a module and using one tool chain, there's a good chance that particularities of that tool chain can be baked into the assumptions of the code, and you'll only have incompatibilities when you try to reuse these modules from a different tool chain, which maybe in theory implements the same spec, but they may actually be incompatibilities, and it's because you're sharing some raw array of bytes. So there's a potential for incompatibilities that only show up late. So to fix some of these, a pretty interesting thing that's kind of lesser known in the protocol space is this Avro. It's in the Hadoop ecosystem. And it addresses these limitations by having explicit schemas that are included in, somehow the protocol and the message stream in the, in the context. And what this allows is there to be a library layer in the middle that performs any coercions when the schemas are not identical on both sides. And so the advantage is this can remove that metadata and coercion code bloat that you needed on the, producer and consumer. And the coercions can be efficient if you are able to statically look at the producer and consumer, and then you can just generate a coercion function that does the necessary mapping. So it can be more efficient. It allows more aggressive representation changes over time because, again, you have this intermediate party. Downside is there's still some fragility that remains because you have this manual deserialization. And you possibly added back the copy that we avoided. So that third copy that we said maybe we can avoid it, well, if you need to do a coercion, you're probably going to need to make an actual extra copy there. So it's an interesting improvement in some dimensions. So kind of all the way to this, on the spectrum is then saying, okay, well, there is no serialization thing. There's only the type values. We're going to remove that intermediate serialization step there. We're just going to send type values directly between the modules. Wins being you can maintain those wins that Avro had regarding API evolution. And you can further avoid this fragility because you have these values that are kind of valid by construction. And it's possible, I claim, to get down to one copy when you do WASM to WASM. So that actually may sound surprising if you have your compiler hat on, because if you look at what I'm saying here, there's an instance A, and then in theory we're producing this value, this tuple of strings, pair of strings that I'm passing to instance B, and you can spot like, well, I could spot 1, 2, or 3 copies in there depending on what those little white trapezoids look like. And so, part of the main work of this proposal is to say that's not the case. So in the trapezoid, it's not just some single instruction that just that has like a fixed input format that you have to like conform to, because that could force the serialization implicitly. Instead, it's code that A gets to write that knows how A represented its source. And on the other side, there's B code that B got to write that knows the representation of B's destination. And this value in the middle is lazy. It doesn't have to be eagerly materialized, which could be another source of copy. And so it's never forced to actually be reified. Instead, when you put all these things together, you can have a single fused copy directly that looks directly at the representation in A and writes directly in the representation in B. And this is a little hand wavy, but I'll be showing how this works in the code later. And this is even true when you have a coercion. If A is passing, a pair of strings and B wants a pair that has, an optional third string, such that there's a coercion function. Both of these values are lazy, and so they can still fuse the whole thing into one, direct copy that doesn't have to make an intermediate. And also possibly zero copy when calling the host. So if A is passing a tuple of strings to the host using its magic host powers can actually look at that A code and say, if that's actually what is compatible with my internal representation, or one of them at least, I'll just hold a pointer, because I can do that. I'm the host. I can just point to that thing in linear memory and not have to actually make a copy. Otherwise, if it's just some kind of arbitrary thing that I understand, well, I can go coerce it into an internal format that the host does understand. So that altogether is a better copying situation. So now trying to turn that kind of hand wavy diagrams into something more concrete, I'll walk through what the proposal is. So I'll start with actually a quick summary of module linking, which this is based on, and then talk about the interface types, and then adapter modules, functions, instructions, and then this interesting fusion concept at the end. So just going to summarize this in one slide. Module linking is its whole own separate thing, but just to cover kind of the relevant bits, what we want with module linking is the ability to perform second-class linking in pure WASM without requiring like the JS API to wire up WASM modules. And this, one of the motivations is to allow pure WASM toolchains to factor out common library code like, say, libc. And we want that second classness to enable engines to AOT optimize and also to avoid an implicit dependency on garbage collection. If you have totally first class instantiation, well, because instances can hold references that are mutable, you can make cycles, and therefore you would require a cycle or garbage collector. It would be a pity if just because I want to factor out libc, I'm now adding to like a fundamental dependency on garbage collection. That's, shouldn't be necessary. If we keep it second class enough, that's not the case. So just to walk kind of through a code snippet using this, let's say we have a module, and one new thing we can do is we can import another module. So this is when I import a module, this is stateless, uninstantiated pure code. I'm not importing any state here. I'm just importing the code of libc. I can, in addition to importing modules, I can nest modules. So here I have a nested module main, which I'll assume has like most of the meat of this of my program here, and it imports an instance of libc, which means it imports a libc that's already been instantiated. So it's importing the state, and it's just saying, okay, I'm going to share this state, and exports let's say some run function. So now, given those two modules, I can first instantiate the libc and make my own private instance that's local to my outer instance. And then I can feed that instance in to make a new instance of main. So here I'm wiring up these instances kind of declaratively, and I get a main instance. And then once I have this main instance, the outer instance can call it. So here you can kind of see the broad strokes. We have module imports, module instance imports, module definitions, instance definitions, and a few other things to wire this all up. So it's rather like ML modules, not surprisingly. If you're familiar with those, it's also designed to look forward to when you're importing and exporting types. An important property is when you import a module, the client has the power to virtualize all its imports. So this is where we see right here when we instantiate this main module, we're controlling all of its imports here. We get to say which libc, which version of libc, which other modules share that libc. And so it gives the client a lot more power than in kind of a more traditional, like a lot of module systems where when you import a thing, you're importing something somebody else has instantiated, and you're usually sharing it with everyone else who imported the same thing. So this is potentially, in some situations, really valuable for all the reasons you want to virtualize. And this is just one slide summary. So if you want to see the full thing, here's a link to the explainer. All right, so that's a foundational bit. So let's look at what are the actual set of interface types. So we start with we have our floats, then we have sized signed integers. There's a character type, a list of any of these things, a record whose fields are any of these things, and a variant whose case payloads are any of these things. And that's at a basic level it. So some notes. Yes, this is the same F32 and F64. That's in the core WASM value types. So the sets intersect, and that's fine. Char, one does not simply have a char without saying what precisely in the world of characters that means. In this case, we've chosen the Unicode scalar value, which means a positive integer in one of these two ranges, the hole in the middle being the surrogates. This is kind of, I think, the most conservative kind of notion that should be allow maximally this char to flow into other languages without causing issues for those languages. The name in the record and fields and variant cases are Unicode strings. So the fields and cases are not identified by order, they're order independent. Type equality for all these value types is structural. And there's no recursive types. If you wanted something like you have to use a list if you wanted something kind of dynamic length. So yeah, so that's our basic interface types that we have for the moment. But we want kind of more. For good language interop, we want a lot of specialized versions of lists, records, and variants. For example, naively, if I have a list type and there's a list of chars, what if I wanted to produce a string value? Naively would just, or not naively, but just the default thing is if a list of anything, if I pass it out to JavaScript would pop out as a JavaScript array of whatever the element type is. So a list of char would produce a JavaScript array containing single character strings, because that would be a list of chars. But what if I want a string value? Do I have to introduce like some special separate string type just so I can distinguish at the boundaries? Because otherwise there's no need. That would be unfortunate. So to kind of balance these concerns, we have this concept of abbreviations, which is sort of lifting the term from the core WASM spec, which to say inside the module abbreviations expand to those previous types I showed in the last slide for all purposes of validation and execution, but at the boundaries you're allowed to treat them as distinct types. So if you're saying how does this coerce into a JavaScript value or from a JavaScript value, you're allowed to treat them separately there. So for example, a string would be abbreviation for a list of char. A tuple could be a record with integral indices where the names are boring. Flags could be a record with Boolean valued fields, which is kind of a nicer alternative to what you usually see as the bit vector in like Wazzy APIs, where it's like, here's an int32, you can OR up all the bits. This could be like a more language neutral version of that. Bool, we've gone back and forth of whether this should be like the scalar type or they could do it as a variant. Currently it's variant. Enum could be variants, without payloads. Option type just between a num and none and a sum, and an expected type to capture the kind of error and not error case. An interesting thing here is languages could say if a function returns an expected, it could actually say the error case turns into an exception where the payload is lifted from that value. That would be an option that language bindings had. And that's if you just had variants, you would never be in a position where you could know, yes, I'll turn that into exception. But if you have this designated abbreviation, then that might make sense. Right. So additionally, interface types have coercive subtyping. Coercive because we're copying them anyways between two things. We can be a lot more flexible if we're allowed to like coerce and change the representation, since we're doing that kind of anyways. So number subtyping would be, if you're injectable, if the destination contains all the source values. List subtyping if the elements are subtype. Record and variant subtyping, kind of the classic depth width, but also allowing reordering. And normally this is not a thing that's fully allowed because you're trying to normally you pass records and variants around, share the, pass a pointer around. But since we're copying anyways, we can just perform the coercion as we're copying it. So it's kind of comes for free, being more flexible. Also, we're considering, defaultable record fields and function parameters, but we haven't written that up in the explainer yet. All right, so those are our types. Where do we use them? If we're using a layered approach.
Luke, we have a question.
Oh, yes.
Salim was wondering how char is encoded, UTF.
Great question. We'll be getting to that in full detail shortly.
That's good.
In a couple of slides, but it's very, very important question. No small amount of time spent on that question. So if we're using a layered approach, where can we use interface types? Let's see, I'll do time. We can't just sprinkle them into core WASM modules. That wouldn't be, that would just be changing the core. So the proposal adds a new kind of module called an adapter module. And it's structurally symmetric to a core WASM module, and that has imports and has exports and definitions. It's just a different set of definitions. In particular, it has a new kind of function called an adapter function. And adapter functions are strict supersets of core WASM functions, and they're extended to be able to use not just core types and instructions, but also interface types and adapter instructions. So whereas you have a core module here on the left that just imports a function and then exports a function using core instructions, an adapter module would say, well, it's an adapter module and it imports adapter functions, and those functions can use strings, which are interface types, in its signature, and it can, in the body of it, it can use adapter instructions. So it's an adapter module. Adapter modules can also contain core module and instance definitions, and this is where we refer back to the module linking spec in the ability to nest modules. So we could say there's an adapter module and it nests a core module. So the blue here is a core module because it just says module. And that's just normal core WASM. And let's say it exports its memory and it has a function run. The outer adapter module can make a core instant, can make a new instance of that. We'll call core. And then it can have an adapter function that takes a string, and then it will use adapter instructions, which will be introduced shortly, to be able to write the string into that exported core.memory. And then it can call core.run. So here's where that kind of adaptation, where it's taking the abstract type into how this module thinks of a string, that's where that happens in that dot, dot, dot. So in particular, if I look at this module, even though the core module does export memory, the outer wrapping adapter module does not. So from the outside perspective, this module does not export memory. It just takes a string. Yeah, they wire up core modules with the outside world. That's their role. And they encapsulate the memories of tables. I said that. So those are the modules and functions. Let's look at the instructions. So this is the where the fun is. Adapter instructions, again, can only be used in adapter functions. Each interface type has a set of lifting and lowering adapter instructions, or that's what the terms we call them. Lifting go from low-level core types to the high-level interface types. They're lifting it up, and then lowering is vice versa. So it's kind of nice, suggestive naming. And as we said earlier, interface values are lazy, and therefore lifting instructions are evaluated lazily, but only these lifting instructions. We'll see a little bit more about that. Whereas lowering instructions are evaluated eagerly, and so where the lowering instruction is where you actually perform that fused copy directly from the source to the destination. So let's start with a really simple one before we get to the fun, which is the char instruction. So char instruction has a lifting instruction that takes an I32 into a char, and a lowering that takes a char into an I32. Some important notes: it traps if you give it an invalid Unicode scalar value. So if you give it, some value outside of that range, those two ranges I mentioned earlier, it'll trap. Therefore, char dot, I should have said lower. Lower is guaranteed to produce a valid Unicode scalar value. But here's the question: if you say I32, are you implying UTF-32? Are you saying that that's the representation of char in memory? No. What we're saying is that I32 is a value on the stack that got decoded somehow, that got to be controlled by the containing code of how I actually pulled that out of memory. So for example, here's a trivial function that decodes a single char from linear memory. So it takes an I32 pointer and it produces a char, and to do that, it gets the pointer and it loads it, a single byte at that address, and then it lifts it. So that would be, for example, how you decode a Latin 1. It's obviously the simplest case, but you could imagine that this could be arbitrarily more powerful branching code to do like load a UTF-8 char. If it's in this range, do this. If it's in that, and at the end of the day, you produce this I32 that has ORed all the bytes that you pulled out of linear memory, and then you char lift that. So that's a single char. It's kind of boring. How do we talk about a string? Well, to do that, we need to talk about lists. How do I lift a list? So lifting list is a lot more interesting. So we have some immediates and some operands here. So this is the type of list we want to lift. These two are functions I'll talk about shortly. We're going to take an arbitrary set of core operands that I get to choose as the embedding function. I get to just say what these types are, and I'm going to produce that list. So so the list is some list of some interface type E. The done, there's two functions. The done function takes these arbitrary T's. So this is my kind of like arbitrary state, my core state that I want to pass in. And it says, am I done? Is there nothing else to produce? And this will be called, before the very first element is produced. So if you have an empty list, it'll immediately be done. And it gets to keep being called, and it produces an arbitrary other set of state. And then there's a lift element function that takes that state produced by done, and it produces an element. So it's going to be somehow having to lift whatever this element type is inside of this function. And it produces the T that's fed into the next iteration. So you have this kind of very explicit propagation of this T star kind of through all these functions. When I lower, it's kind of the opposite. I say, okay, this is the list I'm lowering. Here's my lower function. I'm going to take in some arbitrary state of whatever I want, and I'm going to take in a list interface value, and I'm going to produce some arbitrary state. So where, again, we have this list of some element type. The lower element function takes one single element, and it takes the T star from the previous iteration or the beginning, And it produces some more T star, so it can do arbitrary computation to write this thing into memory somehow. So some important notes here. If you're thinking, wow, that looks slow, calling like 3 functions for every like element, we're assuming in a very fundamental way in this proposal, very aggressive inlining. So this is really being, imagine these functions are just being splatted inline, not heuristically either, just always. And another point is because these are arbitrary code here and arbitrary values, you can lift, and not just contiguous arrays, but like ropes or linked lists or trees, iterators, even things like generators, where this lift element function is calling back into core WASM to actually execute user code. So you can do fairly arbitrary stuff with this, with these instructions. So let's see an example. So I want to make an adapter function that lifts a string, and I'm going to be given a pointer and an end. So that's my low-level state that I get to arbitrarily choose, and I'm going to produce a list of char. And to do that, I'm going to use the list lift instruction for a list of char. I'm going to pass 2 functions I'm about to define. I'm going to pass in my initial state. So the done function, it takes my state and has to produce my state, but also this is a condition saying, am I done? So that condition is simply saying, is the pointer equal to the end? And then I'm just going to propagate the pointer and end state. So I'm just passing it on through. And then when I lift an element, I'm going to take my state that was propagated through right here, and I'm going to have to produce a char, which is the element type, and the state to pass into the next iteration or the next done. So to make the char work, let's assume we're Latin 1 again for simplicity, but this could be a lot more complicated if it was UTF-8. I'm just going to load the byte from the pointer. The pointer to be passed in the next round is adding 1 to the pointer, and then I propagate on the end, so it's effectively a constant for the whole loop. And so that's how I would lift a Latin 1 string. But notice that I could have stuck any other code right here that's a lot more complicated to lift UTF-8, UTF-16, or all the other fun things. So again, I can do a fairly lift arbitrary strings. A classic counterexample when we started this is, well, think about JS engines. Their strings are like, have like a bajillion internal representations. And having worked on JS strings, I think I could be able to lift a JS string with this, with enough branching, with enough code. You could lift directly a JS string, a JS engine internal representation of a string with something like this. So laziness, there's no kind of free lunch. Laziness has its own complications. So what happens if I want to export and adapt, say, this C++ function, right? I have a function that returns a standard string. I marked it as exporting it. The adapter function signature that I'd want, it's be an adapter function that returns a string. Easy enough. That'd be beautiful. The core WASM that gets compiled by like LVM, let's say, has this simplified return type, returns 2 I32s. Let's say it's the pointer and the length, the pointer end. I don't know. In practice, it won't actually probably be multi-value. It'll probably use the stack memory, but for simplicity, it's some I32s. The return memory will get lifted by this adapter function with list.lift, which is evaluated lazily. There's an implicit ABI contract where getName assumes that the caller will free the buffer, because right, this I32 is probably a pointer to some memory that is no longer being held alive by anything else. So it's me, the caller, which is the adapter function. It's my job to free that memory. So how do I do that? I have no idea how the string will be used. So I have no good point in time in my adapter function to say, okay, now free the memory, because when it gets read is some like future point in time. So that's a challenge. So how do we make sure that gets released in all cases? And so to do that, we've extended the proposal with destructors. And so actually there's this extra optional function argument to the list lift called the destructor. And it takes that initial T star, and the guarantee is that this destructor is called when the list is popped. Either when it's consumed by list.lower, in the normal case, or if it's dropped, or if it's popped by some implicitly as part of some control flow that pops the stack. In all cases, the semantics of adapter functions will guarantee this destructor will be called. So based on that previous list string example could have, I could make a free function that just takes the loop state and calls free on the pointer. And then my list.lift will simply say free. And that's it. I don't really have to care who or how the string is used. It will get freed. That's not the end of the challenges. There's another challenge. What happens if an interface value is copied? So there's 2 of them. this raises two sub-questions. First of all, what happens if I copy a value and it has a destructor? Do I call the destructor twice? That just on its face sounds bad. Or do I say, well, the semantics track which one's the last copy and then figure out which is the last copy to be destroyed, and that's kind of but theoretically possible, I think. Another challenge is caused by the same issue is, what if these lift element functions are effectful? If I'm evaluating them multiple times, then the source module will be able to see the side effects multiple times. Like if I passed in an iterator, like a language level iterator, I will see it iterated twice if I just execute this thing twice. So do we specify call by need, which is to say, okay, it's evaluated at most once, which is like the Haskell way. Well, if we did that, it would imply a potential ON temporary copy, because I need to make sure it's the same value henceforth. So I need to have held on to a copy of it. So that's not a good option by our requirements. Do we specify call by name, which is repeated evaluation? Well, this is probably going to break somebody's assumptions, guaranteed over time. So that kind of increases fragility. So can we just disallow the copies? Because all this is sadness. One way to be doing it dynamically and saying, okay, well, there's this dynamic tracking, and then so now there's an invalid state, and we can say, oh, if you try to use a value after it's been taken, it's going to trap on you. But because of our kind of constrained situation, I think we can get away with doing it statically, just with defined type rules. So we say interface types are fine. And to do that, the rules are you can't stick interface types in locals. They can only be kind of on the operand stack. Just avoid the questions of how do you handle local.get. And adapter function parameters, or normally function parameters, are locals just implicitly. Well, we say, no, actually, they're just describing what's initially on the operand stack. So we'll just change the rules here. Incidentally, this is a thing that we considered in the original core WASM, because it's actually a little more elegant, but in practice, it causes just a whole bunch of local.sets to appear at the very beginning of big functions. So it's, it was a mixed thing, but actually, if you look, this is just like way block params work. A parameter of a block just says what's initially on the stack in that block. So it's kind of symmetric. So whereas previously I wrote this with the red is saying, okay, these parameters are local, so I local.get them in the red. That turns into this, where I say, okay, the parameters are on the stack. And then because list.lift just wanted them on the stack, well, I just didn't have to write local.get. They were just already on the stack. So it's kind of, silly, like a point free style. Yeah, so that's the rules. Now, of course, if things are on the stack in the wrong order, another reason people classically use locals to reorder the stack. Well, if we add a rotate instruction, then you can do that, and it maintains the affinity. So that's why I think rotate's a cool instruction. Also to add core WASM, that way you can just import it. It's not like a special adapter thing. So that can make interface types be affine, which gives us a well-defined place that destructors are called, and it avoids all this like repeated lifting question. All right, so we saw the generic list. The generality, I mean, it can capture a lot of stuff, but it has some drawbacks. First is the lowering code can't pre-allocate because it doesn't know the length ahead of time, and that's on purpose. Like if you want to lift an iterator, you don't know the length ahead of time. And also, if we wanted the host to do like 0 copy, you would have to somehow pattern match the lifting code to say, oh, that looks like you're lifting a data structure that I understand, and that's no good. So instead, or to like kind of more directly address these, because these are just instructions and types, we can just add other instructions that can be used instead. There's no reason there has to only be one instruction for lifting or lowering. So we add alternate forms. So we say there's a canonical way to lift a list. And in that one, we're a lot more specific, and we're a lot in saying, okay, well, it's going to come from linear memory. You're going to say which linear memory with a memory index, which is an index to a memory. And yeah, there might be a destructor. And you're going to give us an offset that we're going to load from and a byte length of how many bytes to load, and that will give the list. And based on the type you specify, there will be exactly one canonical way to lift that from linear memory that's specified by the spec. And this is where we're just by fiat just saying there's one way to canonically lift it from linear memory. And now, given a list, you can test, is it actually canonically lifted? So you get this condition saying, yes, it was lifted canonically. And if it was lifted canonically, here's the byte length. So on the receiving side, you have to ask, does this thing have a canonical representation? And if so, you get the byte length, and then you can call lower canon, which is again only allowed dynamically if this list was canonically lifted. But the idea is, because you know it's canonically lifted, you can write it in the same format, and it allows the engine to like massively optimize this. So the lowering code must always test this. It can't assume it's the case, and that means it has to have a fallback to the generic lowering. And so the spec chooses this one canonical representation kind of just by fiat. And this allows the host to specialize for this one canonical representation. So if you want to kind of have this 0 copy fast path, then you would support that. Incidentally, list.lift canon of a string, which recall is a list of char, effectively picks a canonical string encoding. And because that's the general trend that the industry is moving, we picked UTF-8. And so when both sides use UTF-8, what you get is this fused copy and validation loop that can be like really efficient. And what's nice is this kind of provides a general incentive for the whole ecosystem to say, well, if you can, try to use UTF-8 because it's going to be your fastest option. But if you can't, it's not like you fall off a cliff. You have this kind of fine way to lift whatever encoding you happen to have. But it's this kind of general push to say, let's all, if we can, try to use this one canonical representation. Yeah, so it's a complicated design space trying to balance all these how to efficiently do strings, but this is kind of a sort of a compromise point that achieves a number of the objectives. So that was all about lists. Lists are kind of the important one because they're the big ones that can be n large. Variants, I'll kind of go a little quicker here, but you specify what variant you want to lift and what case of that one you want to produce. Where you mention the type of the variance, and then you provide a lift function that lifts that case, which is just kind of symmetric to lift elements, and there's a destructor. And lower, you take the variance and you actually provide a bunch of functions, one for each case, where for each case there's a variant function that takes that payload, and the variant.lower takes care of calling the right function. And so with this, the nice thing about this is because variant lifts only one case, it puts you can use arbitrary core WASM control flow to choose how you lift your different variants. You can use a BER table, you can use BER ifs, or a combination of these things. You can have error returns that are just like return error, and that's if you're returning like an expected, you can just have like your error cases just be single variant lifts. It gives WASM a lot of control on how to lift. Oops, and that's what's nice about them. Records are symmetric and also really boring, so I won't go through them because I'm a little short on time. So, all right. So,
Luke.
Oh yeah, go ahead.
From Luke. What about the non-zero optimization for variants like in Rust?
Oh yeah, that was a specifically considered thing we want to support. So this T star can be like an I32, a single I32, and then actually even before we get there, so let's say the thing flows in from Rust, it's an I32, we branch on whether it's 0. If it is 0, then we can variant.lift the none case, else we can variant.lift the sum case, and then we pass in that I32, and then we have this arbitrary lift case function which arbitrarily unpacks those bits into whatever the payload of the sum case is. And then on the lowering side, you get to choose what this U star is. So you can have both cases. In both cases, all the cases have to produce a U star. So they all, if you want your output to be an I32, you can have all the cases produce an I32 and produce a 0 or a pointer in the sum case. So yeah, that's explicitly supported. Good question. So an observation is when you know the lifting and lowering instruction and you know that they flow together, you can fuse them into pure core instructions. So if I have a list.lift that flows into a list.lower, you can translate that faithfully into a loop that contains as its body these lift elem and lower elem functions themselves fused together recursively. So the question is, what if we could ensure by design that all the adapter instructions can be fused always? Then the semantics of the adapter functions could be defined by just elaborating them into core functions instead of, or in addition, improvably equivalent to kind of the lazy evaluation semantics. If we weren't lowering to core WASM, we would just say, okay, well, here's the lazy semantics. Here's what it means to like evaluate a lift or a lower. We could instead just define it by lowering into core WASM. And similarly, that would be a valid implementation and even preferred implementation strategy. You would just fuse them and then pass it on to your existing core WASM execution support. And so this would realize our goal of being layered on top of core WASM. Up until now, you might have been like, wow, this adapter function sound like not really layered, but just all of core WASM plus extra. And it does look that way. But if there's this step of fusing the adapter instructions to produce the core instructions, then this layering concept kind of comes back. And so that's what I think makes it valid to consider it layering. But how? The one thing to observe is these adapter modules, they don't need to express arbitrary programs. These are really just serving as the trampolines or glue between core modules, which have all the arbitrary code. And so what we can do, which normally you wouldn't be able to get away from, is say, well, adapter functions can only make direct, non-recursive calls, which we can statically require. And when you do that, well, now you can just say, when we're doing fusion, first step is inline recursively until everything's inlined. And so you have one function that's called by core WASM and calls into core WASM. And it's just one big blob of code. And then you can just use interprocedural reaching definitions analysis to say which lifting instructions, which reach, which lowering instructions. And when more than one lifting instruction reaches a lowering instruction, you can generate a case, and each case is a fusion of that lifting with the lowering. And again, this would be very bloaty if you did it for arbitrary programs, but if you're just talking about trampolines, I think you can get away with it. And there's ways to fall back to less efficient ways. But this sort of fusion can smush it all together so that we're always basically doing these lifts and lowers into loops and analogous things for variants and analogous things for records. I'm really glossing over this. There's a worked out example and much more detail and like a pseudo algorithm for this fusion in the explainer. So, all right, that was the proposal. And so now I was going to talk about next steps with my small remaining amount of time. So far, you can use interface types to only pass values, which are immutable, identityless, copyable values. But APIs fundamentally often need to pass handles to resources. There's just no getting around it. Some things just can't be copied, or they shouldn't for size reasons. And they might have identity and state, stuff like that. Files, sockets, buffers, channels, futures, elements of a whole. And if not supported first class, well, then APIs will just simulate it using integers and strings. And that'll be strictly worse because they'll be untyped, they'll be forgeable, they'll have use after free problems. No good. So therefore, interface types must provide explicit support. And so the question is, well, what should that look like? So pretty much since day one, the goal was, let's use the type imports. Let's use abstract types to express resources. So what would that look like? This is an instance type, by the way. An adapter instance would export an abstract type, say call it a file, and then it could export an adapter function that makes a new file by returning a reference to a file. And a close could take a reference to a file, and then a read could take a reference to a file, and also our nice interface types that we've just made. And a write could also do that. So roughly that's, it's this abstract type plus references to it as values is how you would express that. That's like a starting point. And the good thing, this could be implemented by the host or in WASM, which was this goal of Wazzy, is we want to be able to virtualize or implement in WASM all of these interfaces. They shouldn't need to be done by the host. So to implement this, again, in type imports proposal terminology, I could make a type, I could export it, and I would use this private thing, which is more recently added to type imports proposal, to say, I'm actually sticking an I32 in this thing, but don't let anyone on the outside see it. And then using this, if I want to make my new function, and I want to return a file, I can say private.new. I want to make a new file given, let's say I call this core new function, it returns an I32, which is like a pointer to a file, and I box it up into a file, and then I return that as an opaque reference. So you could write that and then close, maybe is the other direction. You get given this reference to a file, and then you do private.get to get the I32, and then you pass that to a core function, which actually does the actual core delete in the linear memory, and so on. But that's, I think, not the end of the concerns. I think there's more concerns that we need to think about, particularly when you have a mixed language modular ecosystem where some of the modules use linear memory and some of them use GC. First of all, to observe resources usually have a lifetime. And it's, I think, important to provide robust safeguards against use after free. Like this example code I wrote here is not robust of against use after free. Once I call close, people can keep calling close and writes, and they'll keep getting that I-32, and it'll just be a use after free. And that's kind of not great. And I can do extra work to try to prevent that, but it'll make my code slower, and not everyone will. So that's I think indicative of fragility if we don't try to provide a more first-class way to prevent that, use after free problem, like at this, semantic level. And second, and I think more importantly, is avoiding any kind of implicit dependencies that would emerge on cross-module GC that you would otherwise have. Like if you have these GC languages, they can be passing like a bunch of references, and that would be cyclic. And then you would just rely on the GC to like see the cycle and collect it all. But then you start adding these linear memory languages, and they're going to root that cycle, leak it forever, and this will only happen emergently after time, and it'll be really hard to debug for everyone. Having worked on a browser with like explicit linear memory and a GC and cycle collection, it's a pain when you have these bugs. You have to have like tools, and we'll be in a strictly worse position in WASM because these modules you didn't write, you don't have their symbols. It's just a big blob of linear memory. You can't see what the structure is inside of that thing. So I think we fundamentally have to enforce, like at a fundamental like spec level, explicit and acyclic ownership. So that's, I think, the remaining and interesting challenges we solved. Following up, just to note, adapter modules, as currently proposed, they don't force shared nothing, they just allow it. That is to say, they allow a mix of core and interface typed imports and exports in the signature. And this enables various practical use cases like Emscripten. If you think about what Emscripten wants, it doesn't want to forcibly be shared nothing. It just wants to use interface types to optimize certain things and then fall back to what it's doing now for all the other fancy things it does. So what if we added a restricted adapter module that did force shared nothing and said, okay, you don't have to, but you can. What do you get if you say, I'm restricting myself to being shared nothing? And let's call this restricted adapter module components, just because it's a nice word. What can this do? What can we do if we actually have this restricted thing at the spec level? One, we can specify that a new component instance got a new WASM store, and a store is like a core semantic concept, which is like the universe in terms of like the spec sense. Well, we could say every component is in its own universe. Step one. Why? Because we're not crossing we don't have any references or other things that normally require you to be in the same universe crossing between the components. Then, once we have that, we can define instructions that make new components and synchronously destroy them. And because we can do that, because we can distinctly say what it means for a store to go away. And if all of our cross component handles are like going through this spec level where we've said what it means, where we've reasoned about lifetimes and said what it means when the other side goes away, we can say it's well defined. If you have a handle to a component and somebody destroys it, it can be well definedly null, or it can well definedly trap. That's just a thing you can specify. At the moment, with raw references, you can't do that. Even more cool, component.new could return a handle to a resource in the sense of the previous slide. So when you have abstract resources, they could be implemented either by allocations inside a linear memory or by whole component instances. So it's kind of a cool abstraction. And if resource ownership is explicit and acyclic, as again previously suggested is necessary, then components wouldn't require GC. And what that gives us is the ability for tool chains to implement things that are currently in Wazzy called commands, which is basically things that I don't want to have long running and executing. I want to like create an instance, call a thing, and then destroy it. And this is like, if I want to invoke grep, I don't want a long-lived grep server, maybe. I just want to like fire up grep, let it run, close it. And this is like sub processes or sub commands, in like a Unix sense. So tool chains can just do that using the instructions. And also we can have this kind of Erlang Midori style many disjoint GC heaps, where each little disjoint heap is a component instance with eager teardown that doesn't require running a garbage collector. You just blow it away because you have this like topological closure of it. So that's the exciting thing. Lots of hand waving there, I know, and I'm rushing. But that's kind of next, and that's it. So there's links, and happy to have questions and happy to go over also if people don't have hard stops. Ooh, 4 minutes over.
Well, thanks, Luke. You packed a lot into 1 hour, which is good. That's what we wanted. At least is what I wanted. Do people have questions? I know I have a question, but I wanted to give other people a chance.
So I don't have a question. I have a remark. The one thing that we didn't add was function callbacks. I wonder if you'd like to speak to that, Luke.
That was going to be my question.
Great. Wow, perfect. Yeah, so we assumed at the beginning callbacks was just a thing we'd have to do because WebIDL had callbacks for one thing. As we discussed, what does it mean to actually, Ross, you actually asked a question. We were like, what happens if that callback has closure state? How does that closure state get deleted? What happens if there's, if it's not GC all the way? How do we resolve these cycles? And thinking through and then generalizing that is what kind of led to this hypothesis that maybe we should require resources to be explicitly owned and acyclic. And when you take that as the basis, a callback that has closure state is effectively a resource. And if I'm giving it to you so you can call me back, that's a cycle, because I'm your client and now and then you're owning something of mine. And so callbacks basically break this, break the rule of being acyclic. So question is, well, then how do, if you disallow callbacks, if that's not a thing you're allowed to do, what do you do instead? And I think with this whole first class stack switching, algebraic effects, this whole thing, we have a really good answer to this, which is you need, where you would have used a callback, you need to kind of transform that into a suspension that you kind of expose to the client as like some sort of iterator thing of, oh, I suspended, back to you. So instead of calling back the client, you suspend to the clients. And if you think about, in my experience, using an API which exposes itself as an iterator always gives me, my client code, much more flexibility to use it than when it calls me back. For example, would you rather traverse an AST with iterators or with some sort of callback visitor pattern? Well, the visitor pattern has all these known problems because it forces you in a very particular route, and any state that you want to wire up has to be in a very specific route. So when you expose your interfaces as iterators, you can have multiple iterators that you simultaneously walk over. You can put it in loops that you control the loop carried state, all that stuff. So iterators, I think, are actually, and that's just one way to transform a callback. There's other ways you would transform kind of publish subscribe patterns. But I think basically the answer is callbacks are bad, and you should instead transform them to resources that kind of return control flow to your caller.
Or simple, I remember I think the simpler case that we described was simply you can give a resource, which is the callback states, and then you just say, call this function with this callback states when you need it, rather than giving a higher order function as the first class thing. If I remember right, but that was months ago. So it's interesting to see that the discussion went somewhere.
Yeah, yes. The resources, if you want a cyclic kind of resource ownership, I think the way to achieve that is to tie that to the module import graph. So kind of resources flow kind of down the dependency graph. If I depend on your module, I can call your functions and you can return resources to me that I own, but not vice versa. I can't pass you my callbacks, but I also can't give you my resources. And so that's kind of how you, I think the way to break the cycle. Yeah, so it's hard to give a callback that has closure state in any case.
Are there other questions?
So is this, the acyclicity constraint is really guiding your design, right? So what's the alternative? What if you didn't, this is essentially to avoid GC, right? Have you thought about what the alternatives would be? A fancy type system comes to mind.
I guess it's hard. Yeah, a sufficiently fancy type system might be able to either prevent cycles. Mm-hmm. I'd certainly be interested in that approach. If cycles are allowed, yeah, it's hard. And if linear, it's this presence of linear memory modules, and you kind of want also the ability to have a module change its representation such that at one point in time it's GC, and then later, whoever decides to rewrite it into Rust. And now it's no longer is a GC language. It would be nice if you could implement an interface as a linear, if linear memory was first class in the sense that you could implement any interface with linear memory language, which you couldn't if you couldn't collect cycle, if you had the cycle problem. So you could imagine trying to make a cycle collector thing where you expose your graph structure to the GC, which is a thing we've talked about in the GC proposal world a lot, and that's fraught with peril, I think. Were you thinking more in the allow cycles but allow them to be collected, or prevent them with in other ways?
Well, so we haven't been thinking talking about cycles so much, but basically what we've been working on, this is my student Michael, who's here. We've been working on a rich type system that allows you to track, take memory that's linear at one point in time and make it GC later, and kind of change between manually managed and GC memory. Of course, that requires a fancy type system. What we have is essentially based on the idea of capabilities. So we have linear capabilities, affine capabilities, and we have a sort of shared capability, which amounts to essentially something being an ML reference, if you will. But there's a whole system which essentially lets you set up a kind of a protocol, right? You can go between the two states. So that might be a flexible way to deal with that kind of situation. The question is, is this sort of requirement of acyclicity a bit constraining, and would you like to get rid of it?
It's a great question and the right time to bring this up, because this is the part that's super unformed yet. We're just literally talking about this right now. So that's the next steps, and that they're still in the highly nebulous state. Of how to do these, how to do these handles. So yeah, I'd love to learn more about what y'all are proposing and read anything you want to send and check it out.
Sure. We should find a time to talk, to meet.
I'd love to, yeah.
That would be great.
Awesome.
All right, and that's Michael right there.
Hi.
Hello.
Yeah, that's exactly the type of thing ideas I was hoping to hear from people, and why I threw in those little saucy things to throw in like at the last moment. It's like all of a rush, but I was like, I gotta get to this point because it's gonna trigger people to like come back and say, well, what about?
Right.
That's an interesting and also contentious idea of acyclicy, that is.
Another thing that we're doing that's sort of related, but is we have this idea of proving soundness of FFIs. So essentially when you have interoperability, but we tend to think about it more directly as interop between two languages. And interface types, of course, is kind of going through, you're lifting to something and then lowering back down. I like how you're framing that as a layering, right? Maybe I would think of it as almost implementing the interface type in terms of the WASM code itself. I often think of it as implementing in the sense of translation or compilation down to just WASM code. Where you implement the conversion functions. So we have, so this is Daniel Patterson. Is Daniel here? Yeah, I think he is. So he's been working on this idea of using semantic techniques to prove interoperability safe. So I'm kind of curious as to how you're approaching the kind of sound interop question within this proposal. And if not, that's something we could help with or think about.
Sound like you mean like there's some invariants that are higher level than interface type about a sequence of calls and like what invariants like that, or something else?
So even with you have certain subtyping rules built in here, right? So even at the level of just proving that those are sound, how exactly do you do that? I guess.
To clarify, by soundness, do you mean safety? What soundness? I think the question.
Safety, yes. The fact that if I do convert, if I do lift and then lower into another language, I will never get anything nonsensical, I guess is the property I'm going for.
That's
safety.
Yeah, that's a really cool thing. I'd love to work with somebody about how to even frame that, define that theorem. So yeah, no, that I haven't done any work there. Also, we don't have a formal semantics yet. This is getting to the stage where the next stage roughly is, I probably should put this next step is to actually start implementing prototype stuff and play with it and see if we can actually like make real WASM modules. And then after that experience, then it would be time, or in parallel, if anyone wants to work with us, trying to formalize the proposal.
Yeah, the idea is that like the fusion sounds to me a lot like cut elimination and logics, and like maybe the sort of higher properties that I think maybe Maul's getting to sounds like sort of natural transformations. You want things to sort of behave well as you can shift between
that's fun.
modules, interfaces, adapters, and all that stuff.
Yeah, essentially, I would put it as, if you're going from a type in a language A to a type in a language B, whether you're going through interface types or the fused version of it, if you start out, if you're converting something from some value that's semantically properly well behaved, like the type here, then you ought to get something. Your conversion function ought to always give you back something that semantically behaves like the type that you wanted here. Or it should always raise an error, right? You shouldn't silently just do some conversion. So that would be safety.
So we had as a mini version of that in when we were looking at lifting and lowering for numeric types, and so lowering can fail. Well, lifting and lowering can both fail if you, and that was that was why Luke put injectable in the requirement.
Yeah.
So there's a notion of like round tripness. Generally, though, the problem that you're looking at is not actually solvable at this kind of level, because nonsense depends on who's doing the interpreting.
Yes, so it depends on what you have two WASM modules, let's say, that you're trying to do this between, but they originally came from some source languages. So unless you keep around type information from the source languages somehow at this level, how do you even know what the source and target types are for that interop? Is that kind of what you were saying, Francis?
No, you don't need that information. You don't need it.
And what did you mean by at this level?
So what is define nonsense, as it were, right? Or unsafe, and at the if the only machine you have is a type machine, then you're limited to predicates like round tripness. So if I go one way and then come back, it should be the same value, which is one of the things that we have tried to preserve. But generally, if I give you a string, it's up to you how to interpret it, and if and you may not interpret it in a way that is consistent with my expectation.
Ah, okay.
Maybe a way sort of like a middle ground is like programs are going to vary a lot, and you sort of like you can't really at sort of the assembly level there is like you're just dealing with bits and stuff like that. It's hard to say bigger properties than round trip and stuff like that. But maybe what Amal was saying was a number of these situations, there are higher level structures there, and so maybe something that could be proved is if you do have programs that came from higher level structures, is the framework you're providing sort of give enough guarantees that it'll preserve those higher level structures? Is that a...
So I think we're looking at a scenario where we don't know the language on the other side. But you would like to establish these properties in the case where you do. All right. So having a round tripness, a round trip property where you do know the types, would be one way of capturing the requirement, I think.
A round trip property, if I lift from here and lower back down, then I want essentially something.
No, if I lift and then lower, you can't see me. Sorry. Yeah, if I lift from A to B and lower, if I lift and lower from A to B and then do nothing but return it, go back, then I should get the same thing that I started with. That would be one way of capturing this requirement, I think. Right. But it isn't actually recapturing the nonsense requirement, because that does depend on higher level layers.
Yeah. Because then the high level layers are telling you what types you had perhaps in the...
Well, your string might be my tree, all right? So they're not even the same type anymore. They're not even recognizably the same. But I just happen to use trees in a string-like way. And so I take your string, map it into my tree, and then you ask for the string back. Well, I'll take the tree and map it to a string. So there isn't any sense in which a tree and a string are the same type, but the use of it is. The use of
right, and it's the interface type which is supposed to somehow give you the agreement, right? How I choose to represent that string and how someone else chooses to represent that string can be very different. As long as we agree that the interface type has the same meaning. Isn't that what we're after?
That's what we've been doing. So that's
Right,
that's why that's what we've been doing. Been defining what these types mean, or they're defining what these types are in terms of primitive types and compositions. But
right, the
there's no,
representations can be entirely different. It doesn't matter at all. But then we should have the round tripping property hold, right?
Well, we certainly hope we have. Yeah. And if we haven't, then we'd like to know.
Okay, cool. Thanks.
Well, it sounds like there's some interesting questions. So I'd be, and I can imagine phrasing various, when you pull into account more of what you know about the higher level language, various properties you might want to state. So I'd be love to hear whatever you're working on there that,
Okay, yeah.
and see, and just try to see if there's anything in the current proposal that goes afoul of it, or, you know, if we just tweak this thing and they would give it, it would let us do this thing that we couldn't otherwise. Like that sort of feedback is certainly valuable.
On a slightly different topic, I noticed that there's only one recursive data structure, which is lists. I was curious about trees, and maybe that's just like a to-do later on.
Actually not. No, we're not doing it.
Wait. And then the other one was the way you recurse over lists is sort of known as catamorphic recursion. And it's very nicely, it's like a very nicely behaved form of recursion, but also like is sort of known to have certain limitations and more complicated recursion patterns. Like it has a hard time with nested recursion and stuff like that. So I just didn't know if you guys have looked at other notions of recursion.
We did. We basically, you know, remember the starting point for this is we're calling function in a different module. We're not actually supporting arbitrary computation.
Yeah.
And so there is this it's informally defined kind of set of types that are maximally reusable across different platforms in different languages. So we're not trying to do all data types. We're not doing hash tables, for example. We're not doing trees and things like that. One reason for that is that in practice, when you have a super complicated type, it's probably not the kind of thing that you, it's difficult to put this in a non-controversial way. It's probably not the kind of thing you should be communicating across a module boundary. If you take a hash table, for example, there's an implied statefulness in most folks' idea of a hash table. There's an implied statefulness to a hash table, so that if I update it, then you see the update. And we're not supporting that directly, except through the notion of a resource, which, as Luke said, is still to be worked out. So if I want you to have access to my hash table, I don't give you the hash table itself. I'll give you a handle to it, and then you can access it through an API, but you can't see how it's built. So there's this sort of, and this is informal. It's not. There isn't like a hard. Doesn't seem to be a hard way of characterizing this.
It makes sense. I was more just curious what the thoughts were, if you guys had thought about these kinds of things or not. So
yeah,
you have. Are there any other?
If anything, the limitations of catamorphins seem to speak to why callbacks are limiting compared to, if I could just iterate over a list, it gives me a lot of power to do arbitrary stuff, to iterate over two lists simultaneously, iterate in really wacky different patterns. But if you're forcing me to supply a function that gets applied for me across a list, it limits me. And so, anyways, part of why I think callbacks are not always the best component interfaces.
I'll point you guys to some of the. I think what you're doing is perfectly fine. There are some other ways of having recursion that still has very strong guarantees, like termination guarantees and stuff like that. And maybe it's just not really necessary. I just was curious if you'd played with it or not. So I can point you to some interesting papers on the topic just to give you some food for thought, but I don't really know if it actually calls for any changes. Are there any other questions that people have?
So one thought that I had during the talk was if destructors sort of necessitate affinity, and then we want to talk about like file handles and things, and maybe this is just a big box of, this could cause a lot of problems, but maybe why not start talking about linearity?
Oh, that's a subtle thing where maybe I'm not even using the terminology, because in some sense we're turning these affine types into linear by saying, well, if you didn't explicitly use it, we're going to use it for you. So like, I don't even know how to express that fact, which is you can like force an affine thing to be linear if you say when it's popped without being used, I'm going to use it for you anyways by calling the destructor.
Okay, that makes sense.
And it's popped up and it popped up in the stack stuff too. We sort of need some sort of fallback of, well, suppose the stack frame just goes missing, or if someone pops it off. Okay, well, you just have to have some destructor for everything in here anyway. So we ran similar problems where you sort of have these technically just affine, but sort of with dynamic linearity enforced.
Right, that's a fun way to say it.
Implicit linearity.
Yeah.
This is very cool. Thank you.
Thanks so much. Happy to follow up with y'all later.
Sounds good. All right. Well, I guess this sounds like a good ending point. So thanks, Luke, for the great presentation. And I'll see y'all in a month to learn about type systems for limiting bounds or bounds checks.